Hi, today I'm joined by Roberto Galeazzi, Associate Professor at the Technical University of Denmark and Head of Control, Robotics and Embodied AI Group. His research focuses on autonomous systems, advanced control, and sensor-driven safety technologies. Today we are going to talk about his team's work on developing and testing autonomous sensor platforms and how those innovations enhance security, efficiency, and resilience in the maritime operations.
Hello, everyone, and welcome, Miroslava, to DTU. Thank you to you and the Maritime Research Alliance for having me.
Thank you. So, what originally motivated your research focus on autonomous systems and robotics for the maritime domain, and why is this field becoming increasingly critical?
Well, when we started this journey, now almost 10 years ago, uh, our drive was to expand access. We saw autonomy in the maritime domain as a way to enable better connectivity for people between mainland and remote regions. The very first project that we attempted to build together with colleagues here towards the first European call on the autonomous ship was actually centered around an autonomous ferry that should be operational here in Denmark to connect some of the islands in the South Funen archipelago with the main island of Funen. And this was truly motivated by the fact that we saw a problem for development of this community because of the lack of continuous connectivity of the existing, of course, man-driven services that, in our opinion, were probably one of the factors why, in general, people around the world is leaving these remote areas and settle in, of course, around bigger cities where, of course, there are services. So we saw autonomy as a potential recipe for substantially igniting a reverse flux from the major, so to say, hubs towards these smaller islands, because in the presence of an autonomous maritime service that could enable, of course, the motion of goods and people, possibly a community could, so to say, reflower again. In connection with that, of course, there was also the wish for working with some very cool technologies. Of course, as researchers, we are also driven by the technological challenge of what we saw already then being possible in the automotive sector. And we wanted to explore what could have been achievable in a maritime setting where some of the challenges are heightened by the increased degrees of freedom, of course, that the vessel has with respect to a car, and and also challenges naturally deriving from the harsh environment where a vessel finds itself to operate with respect again to what a car usually faces. So these two elements have been at the origin of our journey in developing technologies for the autonomous maritime navigation. Today, 10 years later, the field has matured significantly. We find a number of very important technology developers in industry that are proposing products that can be integrated in existing vessels, showing how the entire ecosystem, the academic and the industrial one, have pushed in a quite accelerated fashion to substantially provide initial solutions to enable certain type of autonomous operations in the maritime sector. Autonomy and robotics in general present probably one of the greatest opportunities in the maritime industry today for a number of decisive factors that could alleviate some of the key painful points that the industry is experiencing. First and foremost, we can think about how autonomy could contribute positively to the decarbonization of the industry. Decarbonization will not happen only by finding the magic fuel that will reduce emissions. It's also a matter of optimizing operations on the way to finding such a fuel. Also because the global fleet will not change overnight. So not all vessels will be able to retrofit engines or naturally change towards propulsion systems that are no longer having an heavy carbon footprint. So there will be the need for a number of supporting technologies emerging from the research on the autonomous ship that could enable the optimization of operations. Second, there is the aspect that the industry is experiencing a shortage of labor and skills. So enabling autonomous operations on board vessels is not equivalent to say that humans are no longer needed, but that we can do the same or more with the same amount of people that we have today. And thereby also then increasing productivity and profitability of the business. And then there is obviously the other key pillar, which is enhancing safety of operation. It is not a secret that, of course, ships operates in a challenging environments, and this, of course, exposes the people and the industry in general to a number of unfortunate accidents and incidents. Here is not a matter of pointing the finger at the people on board, because we should remember that the statistics that we see through, for example, the European Maritime Safety Agency are only capturing the unfortunate situation. They don't capture all the events where the timely action and responsive action of the humans have actually saved the day. Here it's about saying, can we elevate the overall level of safety on ship operations by means of smart and advanced technologies, such that we can reduce the number of accidents by simply alleviating the workload on people. Because ultimately accidents more often than not happens because people are overloaded, and thereby they miss at times a critical element that then, of course, lead into an accident. So autonomous ships, autonomous maritime navigation has the potential to contribute to this, let's call it a threefolded industrial revolution in the maritime sector.
Wow. The second question is, GTU's Control, Robotics and Embodied AI group conducts frequent on-site testing. Could you describe what these campaigns involve?
Yes. Here in the research group, from the very beginning, we understood that if we want to develop technologies that have an impact and a value for the industry, we need to test them in the real environment. Developing systems for autonomous navigation is not something that can be done only in our labs by means of simulations. We need physical evidence, both to instruct the research and development process, as well as, of course, to verify and validate that our ideas ultimately generate the value that we advocate for. So in that sense, actually in the last couple of years, we have intensified even more our effort in going out at sea and collecting data. In that sense, we are thankful to our partners that provide vessel of opportunities for us to install our technology, in this case, in particular, so-called multimodal sensor platforms that allow us to collect data from vessels in normal operations, such that we can, of course, learn how, of course, vessels are operated in their daily basis, as well as, of course, stress testing the limits of the different sensing technologies, and once the data are processed, develop new pipelines that can improve robustness of the solutions, the resilience of the solutions, and thereby create, hopefully, real value for the industry.
Testing conditions at sea can be unpredictable. What have you learned from field trials that you could never learn from laboratory simulations alone?
Yes, indeed. What we usually say in research that the simulations are doomed to succeed, and thereby it's only going out in the real environment that you gain the real feeling for the limits of your technology. Testing in the real environment is invaluable. First of all, it gives you access to a volume and a diversity of information that it's very difficult to reproduce through simulations. Of course, nowadays the simulation technology has advanced significantly. No question there. But still, there are elements that are very challenging to reproduce by means of a computer, and thereby to have the capability of collecting a significant amount of data across weather and operational spectra still represent an age. Especially in this field where we're still suffering for significant data scarcity. And then, of course, when you go out at sea and you test your technology, you realize more often than not that you have forgotten a small thing, something that in the lab usually does not come up because, of course, you are not challenged in the same way from the way you need to install the equipment, the way, of course, the vessel moves, and other factors like that, that leads to the emergence of these small things. And sometimes, of course, then it is possible to do some quick fixes. Sometimes, unfortunately, the experimental campaign is not as successful, but there is always a learning experience that we bring back into the lab, such that, of course, the next time we go out and we need to experiment again, we are more robust and better prepared than we were before. And ultimately, the real environment give you that, you will say, the certificate of approved technology. If it works out there repeatedly, then you can, of course, confidently publish your result, confidently present your outcome towards different audience, because you have your ideas backed up from the operational evidence. And today, especially for people like us that work in this area of robotics and autonomous systems, um, regardless of the application domain, experimental evidence represent actually the only key to enter into the rooms, both the academic ones and the industrial ones, where decisions are taken. So in that sense, is extremely important and valuable that we do this job, that we go out and we challenge ourselves, and that we are able to demonstrate that our technology is able to withstand Mother Nature.
What are the main technical and operational challenges you face when deploying autonomous sensor platforms in dynamic maritime environment?
There are, of course, many challenges. The preparation of an experimental campaign is a work of several weeks. It's mandatory, I will say, that if you want to try to be successful, because there is never the 100% guarantee. But if you want to try to be successful in an experimental campaign, you need to go through a very well-established sequence of activities that will lead to a high level of confidence that your hardware will work in the environment, that the software is well, so to say, prepared for managing the hardware and the specific test campaign that you want to carry out, such that when you finally deploy, you have removed, let's say, 99.9% of the potential reasons of failure. Nonetheless, of course, the challenges are not all foreseeable, not all the time. As I mentioned before, we rely significantly on some of our partners through vessels of opportunities to perform our testing. And sometimes small logistical misunderstandings, of course, could lead to unexpected turns in experimental campaigns. In this situation, of course, we always try to gain the most out of it in order to avoid that the work of several weeks is wasted. So of course, also I would say the human communication sometimes can represent or can introduce logistical and technical challenges. Mm-hmm. And then, of course, there is the aspect of testing the technology exactly in the conditions that you would like to go through this type of stress test. Mm-hmm. In the lab, of course, it is always, or it is somewhat easier to develop experiments that are reproducible in nature because you are more often than not in control of the setting. Mm-hmm. When you go out at sea and you test, you are able to control only the parameters that are pertaining your own equipment and your own solution. Anything else is something that you are exposed to and that you need to try to accommodate on the fly. In some of our activities, we will love to capture a specific type of data that maybe are strongly influenced by weather or operational factors, and naturally, it's not always possible to achieve what we want. Maybe mostly on the level of volume and significance that we would like this data to be available, which of course then push back to iterate through these deployments, which of course are at times time consuming, but that's at least at the moment the only way that we see in order to achieve the level of readiness that we need to have and the level of technological confidence that we would like, of course, to push towards our stakeholders.
Mm-hmm. How do autonomous systems change traditional approaches to navigation, monitoring, and safety at sea?
Well, autonomous system technology can and have been certainly disruptive. And here, of course, we should distinguish between what we identify as, let's say, basic automation, which has been present on board vessels for several decades, mm-hmm. to this additional layer of intelligence that enable autonomous navigation. In that sense, of course, the introduction of a much broader set of sensing technologies beyond what is commonly utilized on board commercial vessels, which would be, of course, the GPS, will be the radar, the active system. So the integration, for example, of multiple cameras or even different type of camera technologies, the integration of LiDAR technology or short range radars, mm-hmm. Demands, so to say, layers of intelligent processing in order to make this information consumable to the user. Mm-hmm. People on board are already overwhelmed with the amount of information generated by the standard equipment. Mm-hmm. So they don't necessarily see the need for an additional screen that provides a standalone element or a standalone data point. Mm-hmm. They are demanding for integrated solutions that can elevate their understanding. And that's where autonomous system technologies come and deliver that type of value. And that's, so to say, one of the core research areas here. We are looking significantly into aspect of data fusion and information presentation, relying on multiple sensing devices. And we are also then very much concerned by the fact that as we increase the amount of technologies that eventually ships will welcome in the near future, we are also opening the door to a number of vulnerabilities, mm-hmm. that naturally nowadays come along. And thereby, we in our research, we have a strong focus on what we call cyber physical resilience, which substantially is the provision of algorithms that build on top of cybersecurity measures and that they are looking into what the consistency of information across different sensor platforms in a way that we can thereby monitor the information that is provided to a user and inform at the same time the user about the trustworthiness of this information. Because ultimately, autonomy generates value if the output of these intelligent systems is trustworthy. And the human today, the master mariner, the navigator, has not necessarily the means to assess if this specific data point is true or not. So we need to have technology that can perform this evaluation by itself and then provide, let's say, a guarantee of some sort to the user, say, okay, this information is real, this information is trustworthy, and you can make decision upon it.
Mm-hmm. Your research emphasizes collaboration between humans and autonomous technologies. How do you design systems that support trust, safety, and effective human-machine interaction?
Yes, indeed, the collaboration between humans and autonomous systems is another central focus for us, and I think it should be so for the industry at large. In our research work from the very beginning, we decide to embrace autonomy as an enabler of human capabilities and not a replacement. And in that sense, we have decided that we need, first of all, to understand what is the job that people today do on board vessels. If we want a machine to, an intelligent machine or an intelligent system to elevate the capabilities of a skilled person, we need to understand, first of all, what is the task and the competencies that these people bring to the table. In that regard, we team up, and we're still strongly collaborating with the Svendborg International Maritime Academy here in Denmark, which has provided us with this foundational knowledge that has guided us through the development of a number of solutions concerning the development of situational awareness systems, the development of collision avoidance systems, that were based on the understanding of how humans interpret scenarios, how mariners and navigators take decisions when certain operational settings are presented to them. And thereby, we try to develop technological solutions that are, to begin with, mimicking and then, of course, add the additional, so to say, element that the technology, of course, can process information much faster, that can explore multiple scenarios at the same time, and thereby then providing the user with not just one outcome, but with an handful of outcomes that the user can decide upon, so that the expertise of the people remains central. But again, the intelligent systems that support the navigation elevate their ability to consider multiple options at the same time, and thereby take the best decision, which results as the combination of the human expertise and the machine intelligence.
How does the DTU Center for Cooperative Autonomous Systems support interdisciplinary work across robotics, AI, and maritime applications?
Yes, DTU Center for Collaborative Autonomous Systems represents a gateway for public and private stakeholders to access the rather extensive knowledge base that different research groups at DTU have in the area of autonomous systems. When it comes to maritime autonomy, the group that I'm leading, the Control Robotics and Embodied AI group, as kind of the lion's share here at DTU. We're not the only ones. We have colleagues also at DTU Aqua pursuing autonomous marine systems as an enabler for scientific research in the maritime domain. But essentially, the center is I said, the access point for external stakeholders that they would like to become more knowledgeable in a specific area, or they would like to establish a partnership with researchers or research group here at DTU, in such a way that, of course, as a center leader, I provide these connections and links that external stakeholders need in order to accelerate the the interaction with internal people here at DTU. Mm-hmm. In the maritime context, of course, we, as a, or let's say the center, provide the same type of value, or we try to provide the same type of value whenever there is a stakeholder from the maritime industry that may not be so well acquainted, of course, with our research and development capabilities. I direct these people or these stakeholders towards the right scientific staff here at DTU that can, of course, address and respond their request.
Mm-hmm. Regulatory frameworks for autonomous vessels are still evolving. What are the biggest regulatory or institutional barriers you see today?
There are quite a few, and that's where everybody acknowledges that there is the biggest gap between the state of readiness of the technology and the state of readiness of the regulatory framework. Mm-hmm. As mentioned before, technology has reached already a certain level of maturity. Obviously, we are not ready for what we call the fully autonomous operation, but the different technological building block are already enabling a certain level of autonomous navigation. On the regulatory framework is where now there is a sense of urgency, because as we see in other technological fields, without a clear regulatory framework, it's very difficult for businesses to decide to invest massively in this area. Thereby, it's very important that regulators at national and international level, they push as fast as possible their agendas in order to reach these or a more clear regulatory landscape. If we want to mention some very specific elements that we should keep into consideration, the very first one is that there is not yet an established international regulatory framework for this. IMO, of course, has been working quite intensively over the last 7-8 years to understand in first place what autonomy was about and what value could have brought to the industry. And then, as we know, more recently, they have transitioned from the regulatory exercises into the definition of the so-called mass code. The mass code is almost ready, and starting, I think, from the second half of 2026, it will initiate the non-mandatory phase, which is an experience building phase where operators, ship operators, and the companies that would like to explore the opportunities of so-called mass technology can, of course, benefit from a number of settings, a number of rules that should provide a certain level of guidance. Mm-hmm. But it's not before 2032 that this non-mandatory code will, in principle, become mandatory. Mm-hmm. But the transition between, so to say, the two phases will also build on the experiences of this first non-mandatory phase. Mm-hmm. So there is no, at the moment, to my understanding, there is no firm guarantee that in 2032 the mass code will become mandatory. Mm-hmm. as is. The other regulatory barrier is that it's still very much unclear who is responsible for what. Mm-hmm. And this, of course, if I shall wear the hat of the business owner, it's is what will push me to be very careful about investing massively. Mm-hmm. because if today, when people are on board, it's very clear who is responsible when something does not go as intended. When we start talking about moving people from the bridge to a remote operating center, having software that in principle has a certain level of ability to decide independently, when an accident happens, of course, there will be many question marks. And at the moment, there is lack of clarity about the answers to these question marks. The additional element that I think is worth mentioning when it comes to the regulatory landscape is the lack of specific certification and validation strategies. Many of the technologies that, of course, are supporting the autonomous waterborne navigation are heavily dependent on artificial intelligence solutions. And much of the solutions that are available today are what we call the black boxes. Something goes in, something of interest comes out, but no one really knows and fully understand what is happening inside the box. And obviously, this poses challenges when you want to provide a safety certification of such a technology. Classification societies are, of course, working hard. We are collaborating in a specific project together with Lloyd's Register here in Denmark to try to develop methods and tools, for example, for the assurance of vision-based perception systems. But the problem remains. These are technologies that are very difficult to certify because the underlying methods that they build on, there's what we call the elements of randomness. And thereby, these potential unpredictability makes it very challenging to make a conclusive exploration of what are the limits, and thereby then what could be the safety consequences. The last element that I think is worth mentioning when it comes to regulation is the human element again, because as people eventually will transition into new type of jobs, there is an aspect of what type of competencies these new jobs demands, what type of training these people should receive, and who will be responsible for providing this training. So regulation, of course, are needed also in this setting because the maritime industry is not a local industry, it's a global industry. And ship owners and operators, they find their personnel coming from the all corners of the world. So who is responsible for training? Are the nautical schools that, of course, provide, let's say, the first type of certifications to these people? It will be the flag state where the people are, or where the ship owner has the vessel registered that should provide this type of training. So also these represent an uncertainty because, of course, if we are really looking into a future that has more autonomous and remotely operated vessels out there, it means that the human capital needs to be brought to a level of competence that makes these vessels operational.
How do you collaborate with industry partners, maritime authorities, or other research institutions to ensure your technologies are relevant and applicable?
Well, the collaboration in the triple helix is extremely important. The success of, so to say, technologies in the sense of finding eventually an application in the real world can only be achieved if the academic world is in close dialogue with the industrial world and with the with the regulatory, of course, environment. In our work, what we favor are research activities that are tightly connected with industry. We thereby, whenever possible, we join forces with some of the industrial players here in Denmark and in Europe in order to substantially address some of these remaining outstanding challenges. and thereby try to do a co-development or informed development. The other way to collaborate with industry in situations where maybe it's not possible or it's still too early to involve them is to anyway have industrial players in an advisory board capacity. So that, of course, as we develop solutions, although maybe not mature enough for, so to say, being exposed directly to an industrial setting, we are still able to receive valuable feedback from our industrial stakeholders of what could be meaningful steps as we, of course, advance the state of development, getting more ready for then a real industrial partnership. The same more or less goes on with the regulatory authorities. Usually, of course, the regulator naturally prefers to play the role of the third party and not necessarily being directly involved. But at the same time, to have a continuous dialogue, it's what facilitates the emergence of solutions that are not necessarily always and only challenging the status quo, but also try to embrace some of the good and important elements that are already present in the regulatory space. To make a very clear example, when we have initiated our journey in developing technology for the autonomous ship, it was immediately clear from the dialogue with the national authorities that IMO would never have made a special treatment for autonomous vessels. So from the beginning, then it was clear that autonomous vessels will have to operate on an environment with human-operated vessels. Okay, if they need to be subject to the same rules, then there is no point in developing technologies that elevates these systems to operate above the rules. They need to be compliant to the same rules, and to an external, you would say, observer, they may look like if they were operated by humans, because I can't imagine that we will put a sticker on the hull of these vessels and saying, okay, I'm autonomous. So if, of course, these vessels will engage into any type of de-risking situation, for example, in an event of potential collision, the manned vessels should perceive that whatever this autonomous ship does is somewhat relatable, and thereby, of course, adheres to the same rules, makes maneuvers that are somewhat human-like, and so on and so forth. So in this regard, as I said from the beginning, to have this clear and transparent dialogue with the authorities has pushed us, of course, to make choices down to the level of how we organize our software that substantially was mimicking, for example, the hierarchy that you find today on board the vessel, where, of course, the captain is the ultimate decision maker. There is the navigator who is responsible for the navigation, and this is the chief engineer who is responsible for the machinery. Well, then probably an autonomous systems that should enable autonomous operation on board the vessel should mimic this type of structure and division of roles and competences and responsibilities, because then it's also somewhat easier to, for example, understand when something goes wrong, where the wrong decision was taken.
Yeah. As autonomous systems scale, what do you see as the greatest opportunities and the greatest risk for the future of maritime operation?
There are many opportunities and possibly counterbalanced by the same amount of risks. So we already mentioned some of the opportunities as we open up the interview. There is clearly an opportunity to increase safety of operation. That is one of the key elements that I think accumulates much of the research and development in academia and in industry, a safety element. There is also an element of efficiency. If we can say that an operation today is performed by a vessel, now I'm thinking, for example, inland waterways operation. We have a vessel that is operated by two persons. These people, of course, need to rest. So it means that the vessel will be operational a certain amount of hours during the day, and then there will be a certain amount of hours that probably the vessel is not utilized. If the vessel was to be autonomous, maybe the operation could go on 24/7 with the same amount of people, because then maybe instead of using 2 persons during the entire operation, you need 1 person at a time. In that point, the efficiency significantly increases without producing any harm to the level of employment, and thereby safeguarding both the importance of retaining labor, while of course the ship owner, ship operator can increase its productivity. There is then, of course, the element of decarbonization. As we said before, optimizing operation can be beneficial in supporting the transition towards a greener maritime industry. There is, I still believe, that our starting point, extending access, is still a potential value. If in the future there will be autonomous ferries or vessels on demand, we could actually see that as a vehicle for substantially supporting the development of stronger communities in remote locations. And then there is also an element of creating new jobs. As it has happened in many industries before, when disruptive technologies are introduced, certain type of jobs naturally disappear, but there will be an emergence of a completely new set of jobs that will be, of course, will require a higher level of qualification, but will also possibly put people in more comfortable settings. So that, I think, is also an opportunity that comes along. If we want to list a few risks, there are some that are more evident than others. Of course, the software or the software solutions, the intelligence of these autonomous ships most likely will be able to ensure safety in 99.99% of the cases, or at least that should be the level of ambition. However, also this software is made by humans. So it's not that all of a sudden there will not be the possibility that there is an unforeseeable mistake that will happen. And of course, we need to be careful in trying to assess what could be the consequences of these unforeseeable mistakes, so that at least we are aware that there is still a margin of failure that is possible, and that should be at least acknowledged. As we mentioned already, as the number of sensor and information systems will increase on board vessels, we're also increasing the number of vulnerabilities in terms of exposing the vessel to an increased number of cyber attacks. So, of course, the cybersecurity and the cyber resilience element the security becomes, of course, an element of risk, and thereby there is the need for increased cybersecurity and cyber resilience. The other risk, of course, that is certainly present today is this opacity of the AI-based systems. As we mentioned, CLASS is making a strong effort in promoting the development of methods that could certify the level of safety, but the fact that much of this technology is inherently built in a way that is not immediately explainable what is happening leads to a risk in terms of decodifying in a post-mortem setting why this happened. And if we don't know exactly what is happening inside the systems that are maybe not necessarily deciding but supporting a decision-making process, ultimately we have an actual problem that needs to be fixed. And then as a last risk, I will say the aspect of ensuring that the technology and the governance of the technology are proceeding much more pace to pace. At the moment, we know that the technological development is very much in front of the governance of such a technology and the regulatory landscape that is actually present. We have already mentioned that efforts are happening, but it's very important that we have pretty soon a much clearer regulatory setting, both for businesses to be able to thrive and benefit from the technology, but also to make sure that when something happens, because it's, I think we need to be honest and say that at some point incidents will happen. We are not shutting down, so to say, the technology and development programs because we don't have a governance framework that we're actually from the outset, so to say, prepared for such a type of events, and thereby to have an adaptive way of handling the technology as it progresses, and of course embracing the more mature features, and so to say, establishing testing regimes for the features that instead are still, let's say, not mature enough for coming on board, but that they can still provide value.
And lastly, looking ahead, what message would you most want to share with maritime industry leaders about preparing for an autonomous future?
I have two key messages. I think it's important to understand, and I'm sure that many of our industrial leaders are aware of that autonomy is not just a project. Autonomy is a strategic transition, is a strategic opportunity that the industry has in order to respond to these painful factors that are affecting the industry today. We already mentioned them: decarbonization, shortage of labor and skills, to just mention a few, safety. So in that sense, there is really an opportunity in front of our industry leaders to make a kind of, let's say, small revolution and support the elevation of the industry across these three drivers. And then there is the aspect that we should never forget: the human capital. This transition is not, in my view, meant to replace humans. It's meant to enhance their capabilities to do their job at best. If we, as an industrial ecosystem, we understand this element and we develop in this direction, then I'm confident that we can be successful, because it means that we are embracing the high level of competence, the high level of skills that people are already bringing to the table in their daily jobs, and we are using the technology to further enhance this level of competence and this level of skills, such that, of course, they can be better at doing their job.
Okay, Roberto, thank you very much for our interesting conversation and for your insights and cooperation.
Thank you very much, Miroslava, for having me. It's been a great pleasure.